A power function is a function of the form f of x equals x to the power b, where b is any rational number. We're going to look at a few power functions just in the first quadrant for now. First of all, if b is equal to 2, we recognize that as y equals x squared, which is just a parabola. So it doesn't seem like a new class of functions at first. Also, if b is equal to 1, we end up with just y equals x, which is the identity function, or also is just a straight line. This is a straight line through the origin with slope 1. Once we get into the fractional values, that's where we really see a new class of function. If y is equal to x to the power 1/2, we recognize that as being the same thing as the square root of x. So now these are not polynomials anymore. They do not satisfy the definition of polynomials because they have a fraction power. The square root of x graph is really a parabola on its side, but we only get half of it because the full parabola, which would be x equals y squared, is not a function. When we solve this for y and we only include the positive square root, as indicated here, we just get the top half of a parabola. These three examples characterize all power functions because we can tell the shape of them based on what the power is relative to 1. If the power is greater than 1, then we're going to get behavior that looks sort of like a parabola. It could be something that would grow a bit faster if the power were large, like for example b equals 5. Or it could be something that's a little bit harder to distinguish from the y equals x case. It might grow a bit slower if that power were smaller, like for example b equals 1.2. Similarly, down here below b equals 1, we get this other sort of concavity. The first few graphs I drew are all concave up. These ones are increasing but concave down. So starting at the origin, maybe a power that's between 1/2 and 1, like for example b equals 3/4, would grow a bit faster but still have a downward arc. Right? The way I drew this, it almost looks straight, but we want it to have a slight downward arc. Or if we had a very small fraction, then it would be closer to the x-axis here. It would grow more slowly, like b equals 1/4. All of these pass through the point 1, 1 and the point 0, 0. We can step outside the first quadrant just for some of these fractional powers, since the integer powers are already known. Straight lines, parabolas, polynomials in general, their graphs are already known. But what we're going to look at here are the graph of y equals the square root of x, which I'm highlighting in green, and which is the same, of course, as y equals x to the 1/2. And we'll look at y equals the cube root of x, which is the other graph. Which is the same thing as x to the power 1/3. We can see that their domains don't appear to be the same. This isn't a big surprise, considering that if I try to take the square root of, say, for example, -4, I know that that is not a real number. So -4 is not in the domain of the square root function, and in fact all negative numbers are outside of the domain of the square root function. So we could say that negative numbers are excluded from that domain. However, if we try to take the cube root of, say, for example, -8, there's no problem there. That's equal to negative 2 because negative 2 to the power 3 is equal to negative 8. So there are no restrictions on the domain of a cube root function. The way we generalize this a little bit more is we say it's not just square roots, it's any radical with an even index. If the radical has an even index, our domain rule is that the radicand cannot be negative, and the way we specify that is to state that it must be greater than or equal to 0. If we have an odd index, it's not just the cube root, but really any odd index, then we have no restrictions at all on our domain. And in general, if the radical is the only possible source of restrictions, we would say that our domain is all real numbers. So let's put these new domain rules into play here on these examples. What I have to do is look at this function, identify it as a radical function, and figure out which of these two rules applies. This is a square root, so this is an even index. Even though the index isn't written, it is an implied 2, and therefore I'm going to apply the rule for a radical function with an even index, meaning that I need to take the radicand out. So I'm going to take just the x minus 5, not the square root, and set it greater than or equal to 0. That's my way of saying that it isn't negative. Saying that it is greater than or equal to 0 is equivalent to saying that it's not negative. Then I can just solve the inequality that that results in. X is greater than or equal to 5 is the same as the interval from 5 to infinity. Looking next at the function g of x, we first identify that it has an odd index. Because it has an odd index, no restrictions are brought in by the radical, and x plus 1 has no restrictions on the domain either, and therefore we would immediately jump to the conclusion that this domain is all real numbers. Looking at the graph of the cube root that we have above, we can see that that looks consistent, right? This would be the cube root graph shifted left 1. Shifting left doesn't change the domain if the domain was already all real numbers. So looking at our cube root graph, which is the one in this kind of magenta color up here, we can see that it has domain all real numbers. Shifting it right one should, or sorry, left one should also have domain all real numbers. And finally, looking at h of x, this has an even index. Remember that the denominator of the fractional power is the same as the index of the root, so this is the same thing as saying 2x plus 1 to the power 3 inside a square root, and therefore we will follow the rule for even index here. Setting the radicand greater than or equal to 0 gets us 2x plus 1 cubed is greater than or equal to 0. We would find the 0 and mark it on a number line. The 0 of this is x equals negative 1/2. This is a polynomial inequality that we're solving. So we want to think about where 2x plus 1 cubed is positive and where it is negative. If x is to the left of negative 1/2, like for example negative 1, I can see that 2x plus 1 cubed is going to be negative, whereas if x is to the right of negative 1/2, say for example 0, then 2x plus 1 cubed is going to be positive, and therefore, including only the part of this interval that's greater than or equal to 0, which is the same thing as positive, gives us this interval here from negative 1/2 to positive infinity, and our domain is exactly that, from negative 1/2 to infinity. Note that it would be a little bit of an oversimplification to say that cube root functions always have domain all real numbers. If I make up something like f of x is equal to the cube root of x plus 1 over x minus 5, then it's true that no domain restrictions are brought in by the cube root. So we get no restrictions from the numerator, but it doesn't mean that the whole function has domain all real numbers, because we do get a restriction coming from the denominator, which is that x cannot equal 5. So our domain in this case, either in set builder notation, the set of all x, such that x is not equal to 5, or in interval notation, negative infinity up to 5, union 5 to positive infinity. This is our trick for plucking a single value out of a number line. So that's why we say that the odd index radicals provide no restrictions, rather than going with the slightly simpler message that a cube root function always has domain all real numbers. Cube roots can show up in combination with other situations that may bring in some domain restrictions.